So this is the session of introductory logic called lecture number 5. And in this session, we will complete the introduction of the rules of inference that come in the chapter of how logic works called the chapter called deducing. So these are the rules that permit you to deduce one sentence from one or more previous sentences in your proof. Last time we talked about the rule of assumptions. That's the rule that permits you to write down the givens of a problem. And we talked about two rules that correspond to the propositional connective and the inference rule of and elimination that lets you take away a conjunction, take away each conjunct on subsequent lines, and the rule of and introduction that lets you take sentences that occur on two lines and put those together on a single line with the conjunction symbol between them. In this session, we'll cover 4 new rules. So we will cover 2 rules that correspond to the if-then connective, which we symbolize by the arrow. So the 2 rules there are modus ponens and modus tollens. Then we'll have one new rule that corresponds with the or connective, that upward wedge. So we'll have or introduction. If you're curious why or elimination is not come up yet, why it's not here, we'll see in a subsequent session that or elimination is a more complicated kind of rule. So we'll have to postpone that for a subsequent session. And then finally, well, in truth, we'll have 2 rules corresponding to the negation symbol, but they have the same form, and that is we'll have 2 double negation rules. Okay, so let's just get straight into the material. So or introduction says that if you have a sentence, you are permitted to infer from that sentence the original sentence disjoined with any other sentence whatsoever. Okay, so I've written out an example there for you. So if you start with the sentence, the sky is blue, then you may infer from that the sky is blue or the grass is green, grass is red. I used a false sentence just because it doesn't have to be true. It can be anything. From the sky is blue, I could infer the sky is blue or God does not exist. Or I could infer from the sky is blue, or Harvard is better than Princeton. Okay, so the fact is, no matter what I start with, and no matter which arbitrary sentence I choose, I can disjoin that other sentence. So if you look on the right-hand side of this slide, you'll see an abstract that written down out in abstract form, phi, then phi or psi. Psi is arbitrary, it's whatever you want it to be. And the way that would work in terms of numbering your lines is if this is line M, phi, and then on some subsequent line you write phi or psi, then you refer back to line N, that's your justification, with or, the wedge up symbol, I, introduction. So I've introduced a disjunction. Okay, so now I'll show you an example of this rule in use. Okay, so I wrote down here to show, and then remember what the thing on the right is there. This is this new symbol, this little thing here is the turnstile where the blue arrow is pointing. And the turnstile says there's a valid proof that begins with a premise, the thing on the left, and that ends with the thing on the right on the last line. So what I'm asked to do when I'm asked to show this is to produce that proof, produce such a proof. Okay, so I will begin as usual, my first line, P, here it is, it's an assumption, so I write A. Okay, now I'm not going to reason blindly. I'm going to look at the final destination that I want to get to. The final destination is Q or, and then in parentheses, P or Q. Now, that's a disjunction of Q on the one hand and P or Q on the other hand. I can't get there from line 1. From line 1, I can't just throw everything around P in one step, but I can get there in 2 steps. So what I can do as an auxiliary, I can first disjoin with P or Q, so that's one or introduction. And then I can disjoin with Q again on the left to what I got on line 2. So now I can do Q or P or Q, and that's 2 or introduction. Now that leads to one important clarification. We want to be very precise in how we state the rules, and precisely speaking, disjunction introduction allows you to add the new disjunct either to the right, as we did originally at the top here, or to the left, as we just did from line 2 to line 3. One can or add the disjunct to the left or to the right. So looking back up here at the abstract version of it, we could have gone from phi to psi or phi. So it can go in either direction. Okay, let's do another example of this or introduction really quickly now, interacting with our and elimination. So we want to show now that the disjunction Q or R follows from the conjunction P and Q. So I begin assuming P and Q. Now looking at what I want the end, I want Q or R. I know I can get there using disjunction introduction if I have Q or if I have R. Either one will do. So I look back up at what I have on line 1 and say, what should I use? So P is not going to be useful. P won't do me any good for the conclusion. However, the Q, the second conjunct of line 1, is exactly what I need to get the conclusion. So I'll take Q out of line 1 by and elimination. And then finally, I'll use my disjunction introduction Q or R on line 2 to get the conclusion. And now I've finished that problem. So from P and Q, I get Q or R. Okay, so let's do another example now of disjunction introduction. So in this case here, we're asked to show that this conjunction on the right, P or R and R or Q, follows from the conjunction on the left, P and Q. Okay, let's go ahead and get started here by writing out our assumption, P and Q. And then let's glance to the right and ask what we need to get. So in general, when you need to prove a conjunction, it will always work to prove the individual conjuncts and then put them together using and introduction. That will always work because if you can get a conjunction, you can get each conjunct. So in this case, I have two conjuncts. Here's the first, P or R. Here's the second, R or Q. So I'll just try to get those individually. So I will say, first goal I have in mind here is to get P or R. Okay, now looking back at my conjunction, it should be fairly clear how I can do that. So what I can do is take P out, so 1 and elimination, and then I can disjoin that with R, so P or R, 2 or introduction. That was my first goal corresponding to the first conjunct above. I have now P or R. Now I want to get R or Q. Looking back again at my premise, P and Q. If I get Q, then I have R or Q using disjunction introduction. So now I'll extract the Q from the first premise and then do disjunction introduction on the left on number 4, disjunction introduction. And then finally, now that I've got my second goal, that is I have R or Q, I can put those two things together that I have on lines 3 and 5. So I have now P or R and R or Q. So that's lines 3, 5, and introduction. So now my proof is complete. Okay, so that is our or introduction rule. We turn now to two rules that are both in a way elimination rules for the conditional, that is the arrow, the if-then connective. The first rule is called famously the Latin name modus ponens. Modus ponens says from the assumption that if phi, then psi, and if you add the assumption phi, then you have psi, which of course is just what if-then means. This precisely captures the meaning of if-then. So formally speaking, a line of a proof that uses modus ponens will look like what we have here. In line O, we use line M and N, apply modus ponens, because what we have on line N is the first thing that comes in that conditional. That's what's called the antecedent of the conditional. So modus ponens says if you have a conditional and you have its antecedent, you are permitted to infer the consequent. So the second bit This here is the consequent of the conditional. Okay, so let's see how this rule works in action. So we want to show here that from the assumptions, if P or Q then R and P, we can get R. Okay, so again, I'll write down those assumptions. So P or Q, arrow R, assumption, P, assumption, and I want to get R. Now, 1 and 2 together are not candidates for modus ponens because what occurs on line 2 is not the antecedent of the conditional on line 1. The antecedent on line 1 is P or Q. But of course, P or Q is easily derivable from P just by disjunction introduction. So we can use disjunction introduction on line 2, P or Q. Now we have the antecedent to line 1 and we can apply modus ponens. So 1 and 3 together give R by modus ponens. Okay, so there's a worked proof with modus ponens. Let's do one more with modus ponens. Here we want to show that Q follows from if P, then Q, and P. Together those two give you Q. So again, write down my assumptions. If P, then Q. It's an assumption. And then I'm given P is another assumption. I want Q. Here, the only trick is I'm going to have to apply modus ponens twice because the first time I apply modus ponens to 1 and 2, that gives me P arrow Q. So 1, 2, modus ponens. Now I have P arrow Q on 3, I have P on 2, so now I can do modus ponens again and get Q out. I'm going to be a little careful here with this line, and I'm going to write the numbers in the order where the first number is the conditional. So in this case, it's line 3. The second number is the antecedent of the conditional, in this case, line 2. So that's modus ponens with those two lines. Okay, modus ponens said that if you have a conditional and you have its antecedent, then you may infer its consequent. Modus tollens says if you have a conditional and you have the negation of its consequent, then you may infer the negation of its antecedent. Okay, so that's the sort of case like you said, if it is raining, then the sidewalk is wet. The sidewalk is not wet, therefore it is not raining. So that's a typical case of modus tollens. The format here, as you see, MN, that's the conditional, and the negation of the consequent, and then MT, modus tollens. Okay, so let's see an example of that here. We want to show that from the conditional if Q then, if P then R, and from the conjunction not R and Q, we get not P. So as usual, I'll write down my assumptions, Q arrow, P arrow, R. That's an assumption. Not R and Q, that's an assumption. And I want to get not P. Okay, in this case, with lots of practice, you'll see if you look at what your goal is. So remember I've said before, and I'll say it again, doing proofs requires you to look forward and backwards. Look forward from the premises, what can you get from them? Look backward from the conclusion, what do I need to get there? And gradually, as you look in both directions, you eventually will pull the chain together and then you have a full proof. In this case, I look at my consequent, not P, or my conclusion of my argument, not P. I see it sitting there in my premises. I see it sitting in this conditional here. And it's not touchable yet, right? There's nothing I can do to operate on that yet. So I'm going to have to break things down into smaller bits. In this case, I'm going to look forward. So in other words, I look at my premises, Q arrow, P arrow, R, and then not R and Q. And I see, well, now I can break off the second conditional if P then R because I have the antecedent Q to that longer conditional. So I'll go ahead and write that down. I'll go ahead and put Q derived from 2 and elimination. And then I'll apply that to the first line using modus ponens gives me if P then R. So 1, 3 modus ponens. And now I'm just going to reevaluate. do I have enough to get myself not P? I have P arrow R, that's good, because if I have not R, that is a candidate to apply modus tollens. Now, of course, I do have not R, it's just hiding in that conjunction. I'm back up on line 2, so let me get that out. So take not R out of line 2 by and elimination. And now finally, I'm in a position to apply modus tollens to 4 and 5. So not P, 4, 5, modus tollens. Okay, last pair of rules for this session are the double negation rules, which are the easiest rules imaginable. From a sentence, phi, you can add 2 negation symbols. So it's the principle not is the same as positive. 2 negatives in this case makes a positive. So from phi, you can infer not phi. And then on the right, as you see, from not phi, you can infer phi. So you can just take off 2 negation symbols. Now, this rule will in many cases be very useful so that you can follow the other rules precisely without error. Because the thing is, we must follow the logical rules to the letter. So that is, for example, if I ask you for the negation, if I say, what is the negation of not P? The negation of not P is not P. The negation of not P is not P. So if you negate not P, it's not P. Okay, so now that can be, you can prove P from that, and you can prove that from P, but they are different syntactic entities. Okay, so let's look at an example of the use of double negation. So we want to show that from P arrow not Q and Q, we can get not P. So I'll write down my assumptions, P arrow not Q, assumption, Q, assumption. Now I want not P. Now, the following is going to seem like a fairly trivial point. It will seem to some of you as pedantic, that is overly worrisome about the syntax of the rules, but that is the point of logic. The point of logic is precision. 1 and 2 here, you cannot, as it stands, apply modus tollens, because modus tollens, the letter of the law says, if you have a conditional and you have the negation of the consequent, the negation of the thing after the arrow, in this case, that is this right here. So this is the consequent, is not Q. So if you have the negation of not Q, then you may infer the negation of the antecedent, which is P in this case. That is what we want. We want the negation of P. We want not P. But Q is not the negation of not Q. Not Q is the negation of not Q. So now, to be precise, we come back and apply double negation to Q. So 2 double negation. Now lines 1 and 3 do fit the pattern for modus tollens. So on line 4, I can put not P, 1, 3, modus tollens. Okay, so now on the problem set you have at hand to work on, will give you problems that throw together all of these new rules of deduction you've learned. So you'll have problems where you have to apply conjunction, introduction, elimination, problems also modus ponens, modus tollens, double negation rules, and or introduction. So we'll mix those all freely together. But in general, as long as you follow the advice that where you reason forward from your premises, you apply the rules you can, you keep your conclusion in mind and ask what you need to get, these proofs will be straightforward. Let's do one more example to conclude today. That is, we're going to show that from this conditional, that is the conditional whose antecedent is not if P then Q, and whose consequent is Q, and then from the sentence not Q, then we can get not P. Okay, so write down my assumptions, not P arrow Q, that's an assumption. And 2, not Q is an assumption. Okay, now keep in mind that I want not P, but looking at premises 1 and 2, it's not obvious how I get not P, because P is sitting inside 1, but it's inside the parentheses It's untouchable right now. Okay, what I can do is if I look at lines 1 and 2, it should stand out to me that it's a candidate for modus tollens. So I can apply modus tollens to 1 and 2. That will give me the negation of the antecedent on line 1. So I would get not, P arrow Q. So 1, 2 modus tollens. Now, I'm starting to see where I'm going because now I have not P arrow Q. I want to get not P. I have not Q. So if I can get P arrow Q, then I can apply modus tollens again and get not P. Fortunately, not, and then in parentheses, P arrow Q is, from that you can derive P arrow Q by a simple application of double negation. That is, of course, so 3 double negation. That is, of course, why it's important that the rule is schematic. That is, it doesn't say from not P you can get P. It says from not anything you can get that thing. Not phi you can get phi. In this case, our phi that we get apply not to is P arrow Q. So P arrow Q is doubly negated, and we can take both those negations off. That gives us P arrow Q. Okay, and then finally 2 and 4. In this case, I'll write my lines this way because modus tollens, the conditional is in line 4, the negation of the consequence line 2, so that gives me not P from 2 and 4 modus tollens, 4 and 2 to be precise. Okay, so these are our rules for deducing. Applying these, you'll be able to solve any of the problems in the current problem set.